At the center of almost every large galaxy lies a supermassive black hole, millions or billions of times the mass of the Sun. When two galaxies merge, their black holes enter a dance, spiraling inward toward an eventual collision. As such massive objects move, they bend the very fabric of the universe, generating gravitational waves. Like dropping a rock into a pond, these waves ripple outward, but instead of producing peaks and valleys on the surface of the water, gravitational waves deform space and time. In 2017, scientists detected gravitational waves that passed through two detectors with laser arms 4 kilometers long. The ripples in space-time changed the way the laser beams overlapped, which was picked up by a super-sensitive detector. Despite the impressive precision of this device, it's only able to pick up the types of ripples that come from the mergers of small black holes, or neutron stars. To detect gravitational waves from much heavier black holes, like the ones that anchor galaxies, they would need laser arms too large to even fit on Earth. Instead, astronomers have come up with a clever workaround by turning dozens of dead stars, called pulsars, into a giant laboratory. Pulsars are rapidly rotating neutron stars that shoot out beams of radiation from their magnetic poles. As the pulsar spins, those beams flash toward Earth like a lighthouse. Some pulsars revolve a few hundred times per second. The sweeping beam arrives with incredible regularity, making each pulsar like a precise metronome in space. Astronomers have been monitoring dozens of these pulsars in different directions to help search for gravitational waves. They call these networks pulsar timing arrays. The idea is that when gravitational waves from merging supermassive black holes pass by these lighthouses, they change the distance between the pulsars and Earth. Some get a tiny bit closer and others get a little farther from us. That means their rhythmic flashes appear to get a little faster or slower. The pulsars act much like the laser arms on the ground. The difference between when we expect the flashes to arrive and when they are actually detected is the signal of gravitational waves. Because the pulsars are so distant, the light has to travel much farther than it does in the lasers. That means this method should be sensitive to gravitational waves with longer wavelengths, like those from supermassive black holes. Identifying a specific black hole pair with this technique is really difficult. So the first objective is to find the background hum of all the supermassive black holes combined, the so-called gravitational wave background. In January 2021, scientists announced the first evidence for such a hum, but they haven't been able to prove it's actually from the gravitational wave background. Several pulsar timing arrays are currently hunting for a telltale pattern in the hum that would allow them to claim their detection. If the search proves successful, nature's lighthouses could help illuminate some of the darkest, most mysterious objects in the cosmos.